Welcome to Solving Equilibrium Problems. So, the procedure for solving equilibrium problems is step 1, write the balanced equation for the reaction. Step 2, write the equilibrium expression. Step 3, list the initial concentrations. And step 4, calculate Q, the reaction quotient, and determine the direction of the shift to equilibrium. Step 5 then is define the change needed to reach equilibrium and define concentrations by applying the change to the initial concentrations. Step 6 is to substitute the equilibrium concentrations into the equilibrium expression and solve for the unknown. And step 7 is to check your calculated equilibrium concentrations by making sure they give the correct value of K, the equilibrium constant. So let's look at an example of the synthesis of hydrogen fluoride, HF, from hydrogen and fluorine gases. So suppose 3.000 moles of hydrogen and 6.000 moles of fluorine are mixed in a 3.000 liter flask, and the equilibrium constant at this temperature is 1.15 times 10 to the 2. The first step was to write the balanced equation for the reaction, and that means that we have an equation that looks something like this. Note that this box should be a double-headed arrow, the equilibrium arrow. So we have the hydrogen reacting with the fluorine to give us HF, hydrogen fluoride. So now we can write the equilibrium expression. We know that the value of our equilibrium constant K is equal to 1.15 times 10 to the 2. And we know that that has to be equal to the concentration of HF squared divided by the concentration of hydrogen times the concentration of fluorine. And now we want to list the initial concentrations. So here we've got this subscript 0 or naught. So that's the initial concentration, or at time equals 0 for our species. We know that we have 3 moles of hydrogen divided by our 3 liters gives us a concentration of 1 molar. We have 6 moles of the fluorine divided by our 3 liter volume gives us a concentration of 2 molar. And initially we start out with none of our HF, so we have an initial concentration of 0 molar for the HF. So the next step was to calculate the Q, the reaction quotient, and determine the direction of the shift to equilibrium. So Q, the expression for Q, again, is the same as the expression for K, except that for K, we have to plug in the equilibrium concentrations of our species. For Q, we're plugging in, we don't have to plug in the equilibrium concentration. So now our value of Q then is equal to our concentration of HF squared, so 0 molar squared, divided by our concentration of hydrogen, 1 molar, times the concentration of the fluorine, 2 molar. And that means that now we have 0 molar divided by 2 molar, which gives us 0. And that means that Q is less than K. This is not surprising, because if we have none of our product, then we can't possibly be at equilibrium, because regardless of what the value of K is, it can't ever be 0. So this means that our system must shift to the right. We must make some more of our product, which shouldn't be surprising, considering that we started with none of it. So the next step was to define the change needed to reach equilibrium and define concentrations by applying the change to initial concentrations. What this really means is to make an ICE table, right? Remember that ICE, ICE stands for initial, change, and equilibrium. So our initial concentration of hydrogen is 1 molar. Our initial concentration of the fluorine was 2 molar. Our initial concentration of the HF is 0 molar. The change in hydrogen concentration, well, that's going to be minus X. The change in fluorine concentration is going to be minus X. Note that if we have a coefficient here, then we would have that coefficient also written down there. The coefficient is 1 here, so there essentially it's minus 1x. Here we have a coefficient of 2, so here we're creating, so plus 2x. Note that for the reactants it's minus x or minus 2x or whatever. For products it's going to be plus x or plus 2x in this case. So then at equilibrium we have whatever we started with, the 1 molar plus whatever the change is. In this case, the change is negative x minus x. So we have 1 minus x there. We have, so this should be a 2 minus x for our concentration of fluorine. And we have our initial concentration of 0 plus 2x, so just 2x for our HF concentration. So the next step is substitute the equilibrium concentrations into the equilibrium expression and solve for the unknown. So again, we know the value of K. So when we plug in, we have concentration of 2x for the hydrogen fluoride. That needs to be squared. And then we divide by the concentration of hydrogen, that's the 1.0 minus x, times the concentration of fluorine, 2.0 minus x. And now I'm then going to, so now we have 1.15 times, or rather is equal to this fraction. I want to then take the denominator and move it to the other side. So we have the 1.15 times 10 to the 2, that's the value of K, times our denominator. And that has to be equal to 4x squared. Remember that you have to square the 2 and the x. And then I multiply these two parentheses by each other to give us this bottom line here. And so you see that we have a quadratic equation. Then I multiply the 115, note that that's the 1.15 times 10 to the 2. Distribute the 115 through, and now we get this line. And note that in also I've distributed the 115 and then I've moved this 4x squared to the other side. So now I have the 115 times this set of parentheses, and then I'm minus 4x squared, and that's now equal to 0. So now I've got that quadratic expression equal to 0, and now we can use the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And we can plug in the values. Remember here that 111 is a, the negative 345 is b, and the 230 is c. Note here that in order to keep track of sig figs, I've placed this decimal point there in 230. You're free to put that decimal point in or not as you choose. So when we plug in our A, B, and C values and we work out the math, we end up with two values. We end up with either 2.14 molar or 0.968 molar. So whenever you use the quadratic formula in this way, you're always going to get two values. Now, one of them should, at least hopefully, be a nonsensical value. And we need to figure out which of our two values it is. So, we have a value that's 2.14 molar and one value that's 0.968 molar. So, X has to be one of those two values. But we only have 1.000 molar of hydrogen gas, which means that we can't react 2.14 molar of hydrogen gas because we don't have that much. So once we get to 1 molar, then the reaction has to stop. We can't react that much of it, which means that that 2.14 molar is a ridiculous value, so we have to throw that one out. So if we throw out that value, the only value we have left, the only possible value of X that's remaining, is this 0.968 molar, which means that that's how much of our hydrogen we're going to react, and now we're not left with very much. So if the value of X is 0.968 molar, that means that we know that we have, at the end, 1.000 molar minus X molar. Well, that's 1.000 molar minus 0.968 molar, which means that we have 0.032 molar remaining of the hydrogen. And we'll end up with 1.032 molar remaining of the fluorine. And that means that for the HF, because we're producing 2X, then we started out with 0 molar of the HF, and we're producing 2 times 0.968 molar, and that means that we end up with 1.94 molar of the hydrogen fluoride. So the last step then was to check your calculated equilibrium concentrations by making sure that they give the correct value of K, the equilibrium constant. So when we plug in our values, 1.94 molar of HF, quantity squared, divided by 0.032 molar for the hydrogen, and times 1.032 molar for the fluorine. That gives us 114. That's pretty darn close to the 115, or the 1.15 times 10 to the 2. Note that it's slightly off because I've rounded here for the 3 concentrations. So again, there's some slight rounding error in our calculation, but it's pretty darn close. So that was solving equilibrium problems.